Welcome to Maths with EJD. In this video, we look at Laplace transform for differential equations in electrical circuits. Okay. Um, let's have an overview of this. Again, we know that the Laplace transform is a powerful tool used to solve differential equations, especially in the analysis of electrical circuits. In the analysis of electrical circuits, okay, by converting differential equations into algebraic equations, the Laplace transform simplifies the analysis of circuits, particularly those involving resistors R, inductors L, and capacitors C. So let's look at a case of RC circuit where we have resistor capacitor. That's the RC circuit. That's resistor capacitor circuit. Resistor capacitor. Oh, okay. Let me write it this other way. So resistor capacitor, or what we can call RC circuit. Okay. So for an RC circuit, the relationship between voltage V of t and current I of t is governed by the differential equation V of t equals Ri of t plus 1 over c integral I of t dt. So in this case, we can take the Laplace, taking the Laplace transform of both sides, assuming zero initial conditions. So anywhere you see any initial condition, you just take it as zero. Okay. So in that case, we get the Laplace of V of t to be equal to R L. There's I there. So R then the Laplace of I of t plus 1 over c. Then we take the Laplace of the integral of I of t dt. I mean, when we started out, we saw the possibility of taking the Laplace of integrals. Okay, so since the Laplace transform of an integral is L integral I of t dt is equal to 1 over s I of s. Okay, that's I over s like that. The equation becomes V of s equals Ri of s plus 1 over Cs I of s. Okay, so that is what we have. Of course, we can go on factoring, since we can make it in terms of current, factoring out I of s. You know, you have I of s here and there's I of s here. So we can get V of s all over whatever is left. Okay. I mean, factoring out I of s, we can even do that. So that's V of s equals R plus 1 over Cs into I of s. So which makes that we have I of s equals V of s all over R plus 1 over Cs. And that's in the S domain, where everything is now algebra. So we can find the current this way, and we can also find the V of S as far as we have the information we need. So this gives the Laplace transform. This gives the Laplace transform of the current in the RC circuit. So to find the time domain current, that's I of t, right? We would take the inverse Laplace transform of I of s. Okay, so let's take an example of that. Example, consider an RC circuit with resistance 1 ohm, current is 1 F, and a voltage source V of t is equal to 1 volt, that which is a step input. Okay, the Laplace transform the Laplace transform of the voltage is V of s equals 1 over s, and then the current I of s in the circuit is I of s equals 1 over s all over 1 plus 1 over s, and that is 1 over s plus 1 altogether, right? Because the current is 1F, right? And we have to integrate that in the system. So we have this. So taking the inverse Laplace transform, So we just see that I of t is equal to e raised by minus t. Thus, the current in the circuit is I of t equals e raised by minus t. That's what we have in that situation. Okay. So that's for an RC circuit. Let's check for what happens in the case of an RL circuit. So resistor, inductor, or what we know as an RL circuit. So here, for an RL circuit, the voltage current relationship is described by the equation V of t equals Ri of t plus plus the inductor, right? L di of t dt. Okay, so taking the Laplace transform, taking the Laplace transform of both sides, we have L of V of t, and that is equal to R L of I of t, then plus L, the normal inductor, and the Laplace now of di of t dt. Okay, so in this case, we now have V of S, right, in the S domain, and Ri of S for this now in the I to S domain, and then plus L. Now, this is a first derivative now. So in this case, we are going to have, of course, L is out here into, so when we split this up, we know that's going to be I of S minus I of 0. Okay, so if we take I of 0 to be 0, like as usual, like when we assume, so assuming the initial current is 0, so we just have V of S equals Ri of S plus Li of S, because this will just go to 0, and this is what we end up having. So we can factor out I of S. So we have R plus L. Okay, there is something. Okay, yes. So this should be Si of S, just like we do. So this should be L. So this is LSI of S, very important. This is LS. So from what the kind of thing we've been doing before. So we have I of S. So in this case, we now have I of S to be equal to V of S all over R plus LS. And this is the relationship in that algebraic domain. For example, consider an RL circuit with resistance 1 ohm, inductance 1 Henry, I think, and a voltage source. V of t equals 1 volt, which is a step input again. Okay, the Laplace transform, the Laplace transform the Laplace transform I of t equals e raised by minus t. Okay, the Laplace transform, Laplace transform of the voltage, sorry, of the voltage V of S is equal to 1 over S because the voltage is 1, so we have 1 over S. So, and for the current, okay, let me, Laplace transform for the voltage is V of S equals 1 over S. I have that. Okay. And for the current is I of S equals 1 over S all over 1 plus S. And that is equal to 1 over S plus 1 as usual because the current goes that way. So taking the inverse Laplace, taking the inverse Laplace transform, so we have I of t equals e raised by minus t again. Thus, the current in the RL circuit is I of t is I of t equals e raised by minus t like before. So, yeah, that's an example to support that. So finally, let's go for an all-encompassing circuit. Let me switch over to green, and then we have, okay, let me even do this, and then we have, say, green here. So let's talk about an RLC circuit. That's a resistor, inductor, capacitor, RLC circuit. So here, the RLC circuits voltage current relationship is given by V of t equals Ri of t plus L the I of t dt plus 1 over C integral I of t dt. Okay, so if we take the Laplace, taking the Laplace transform of both sides, we now have, that's, I mean, we've done this a lot, so I'll just go straight. So we have V of S equals Ri of S plus Ls I of S minus L I of 0, then plus I over C 1 over S I of S. That's when we integrate like that as we had it in the first case, right? So with this done, if we now assume, so assuming initial conditions, I of 0 equals 0 and the I of 0 dt is also equal to 0. We have V of S. So in that case now, this will be gone, right? So, and we have IS running across RI. So if you factor out I of S, we have R plus LS plus I over CS. Okay. So V of S now will just be R plus LS plus 1 over CS, then I of S out here, so that I of s will now be V of s all over L. Okay, if we take LCM, right, with that, so we have L s squared. Okay, I mean, first we can just have this. So we have R plus LS plus 1 over CS. So we can just have it this way. And we may also try to tidy that up as much as possible. Um, so if we have R over 1, LS over 1, so we can have I of S equals V of S all over the LCM down there will be okay, I think if we just take mm, okay, yeah, I guess let's just leave it the way it is up there. Let's leave it the way it is here so we don't complicate issues further. So this is clearly what we get in this situation. So this is the general form now. So this is the general form for the current in an RLC circuit. The solution, the solution in the time domain can be found by taking the inverse Laplace transform. Okay, so example, consider an RLC circuit with resistance 1 ohm, inductance 1 Henry, capacitance 1, I forgot what this F is, and a voltage source V of t equals 1V as a step input. Step input. Okay. The Laplace transform, as usual, the Laplace transform of the voltage is V of S equals 1 over S. And for the current, we have I of S equals 1 over S all over S squared plus S plus 1 using partial fraction decomposition, which we've done a lot. Using partial fraction decomposition, okay, and inverse Laplace transforms, we can solve I of t. In this case, the time domain solution corresponds to a damped oscillation. Okay, please take this as an assignment. So, let the assignment be to get I of t. Okay, get I of t. Let this be the assignment in this situation. Get, okay, normally here we say I of t, right? That's smaller. Get I of t. So this is practice. Get I of t from that. Okay, so of course, like we said, in this case, the time domain solution corresponds to a damped oscillation. So in conclusion, we see that the Laplace transform simplifies the analysis of electrical circuits, turning complex differential equations to algebraic equations. The process involves taking the Laplace transform of the circuit's governing differential equation, solving for the Laplace transform of the current or voltage, taking the inverse Laplace transform to find the solution in the time domain. And this method is particularly useful for circuits with resistors, inductors, and capacitors, where differential equations commonly arise. So that's how we have it in this video. Don't forget the practice. Find I of t from this expression of I of s from the RLC circuit. Okay, let that be the assignment. Let me see that in the comment section, either on Facebook or on YouTube. And of course, let me also know that if how helpful these videos are for you, and if there's a topic you'd like me to teach or a problem you'd like me to solve. If you have not subscribed to this channel, you'll be missing a lot. So please go ahead and subscribe. And if you have subscribed and with together with those who will just be subscribing, don't forget to hit the notification bell so you can always get alerted each time a new video is released. Then, of course, like and share so that more people can have access to this great content we have here. Until I come your way again, keep doing maths right. Bye.